Chapter 3, Stoichiometry. Our outline is atomic mass, mole, molar mass, percent composition, empirical and molecular formula, chemical equations, stoichiometric calculations, and limiting reactant. Atomic mass is a weighted average. So to get into what that means and how to work with it, we're going to consider this example. Let's say we need 1,000 nails. The bin that the nails are in contains two types of nails, nail A and nail B, with different masses and abundances. And there is a balance for us to weigh the nails. So we will count by weighing. So we need to figure out how much we need to weigh out. Nail A has a mass of 3.1 grams, and of the nails in the bin, 20% are nail A. Nail B has a mass of 2.5 grams, and 80% of the nails are nail B. So what we're going to do is calculate the weighted average mass of a nail. That weighted average mass is the abundance divided by the 100. We're getting rid of percent. So it'd be the abundance of nail A times its mass plus the abundance over 100 of nail B times its mass. We can't just simply average 3.1 and 2.5 because their abundances are not equal. They're not 50%. There's more B, so the mass that we ultimately weigh out to get these 1,000 nails is going to be a little closer to using the 2.5 gram mass. Alrighty, so our weighted average mass is 20 over 100 times 3.1 grams plus 80 over 100 times 2.5 grams, giving us the weighted average for the nail to be 2.6 grams. Note that neither nail weighs 2.6 grams, but since we're counting out by weighing 1,000 nails, that is a combo of the two with those 20% and 80% abundances, we're acting like that's the mass per nail. That's the weighted average mass. So to calculate how much we need to weigh out, we take our 1,000 nails and we multiply by our conversion, which is 2.6 grams per nail. Notice that we write it in such a way that nail cancels out and we calculate the unit to be gram. We get 2,600 grams. So we weigh out 2,600 grams. It'll be 20% nail A, 80% nail B, and it should be 1,000 nails or close enough for our work. Okay, now how we apply that to atoms. Atoms come as, for a particular element, oftentimes we have more than one natural isotope of that element. For example, with carbon, it comes primarily as carbon-12 and carbon-13. The mass of carbon-12 is 12.000 U, atomic mass unit, and the abundance is 98.89%. The other main isotope of carbon is carbon-13 with an abundance of 13.003 U. The abundance is 1.11. Notice that because we're just considering those two isotopes of carbon, their abundances add to 100%. 98.89 plus 1.11 is 100. So the weighted average, the atomic mass of carbon is then the abundance over 100 of carbon 12 times its mass, plus the abundance over 100 of carbon 13 times its mass. So we have 98.89 over 100 times 12.000 U plus 1.11 over 100 times 13.003 U. And we get the atomic mass to be 12.01 U per atom, or simply 12.01 U. Notice that neither atom has a mass of 12.01 U, but since we count atoms by weighing, we need to work with the weighted average, the atomic mass of that element. The periodic table shows the atomic mass of each element. For carbon, you would see 12.01 and then some more figures. Here's an example. Calculate the atomic mass of lithium. You're given the two isotopes of lithium. Some elements have more than just two isotopes. Some even only have one. Anyway, lithium has these two, and we see their abundances. Notice again that the abundances would add to 100%. Here's the next problem. Europium is composed of two isotopes. We're given the masses of each isotope. We're also given the atomic mass of europium. It is 151.96 U. Our problem here is to determine the abundance of the 151 isotope. We're after the percent abundance of that one. So it's a little different than the problem that we just did with carbon or you did with lithium. That is, what we know about it is atomic mass and masses of isotopes. The abundance of the two isotopes, realize the net abundance is 100. So the abundance of the 151 plus the abundance of the 153 adds to 100. Take that into account as you do this problem. The next topic is the mole. In the lab, we work with quantities of chemicals that we can hold, we can see, etc. And yet we also know that atoms are so tiny that we cannot see them with our naked eye. What we have to do is work with large quantities of them in the lab. Quantities often come to be like 10 to the 23rd atoms of an element or molecules of a sample. Huge amount. A mole is a quantity, kind of like a dozen is a quantity. 1 dozen is 12. 1 mole is 6.022 times 10 to the 23rd items, be they atoms or molecules or whatever. It's just a quantity. It's a huge quantity. It's such a huge quantity that if we had that many marshmallows and we were surrounding the earth with them, we would have to go 18 miles high in our marshmallow covering of the earth to be able to lay down all the mole's worth of marshmallows. The significance of the mole is a sample of a natural element like carbon with a mass equal to the element's atomic mass in grams contains 1 mole of atoms. Okay, let's prove this by calculating the mass of 1.000 moles of carbon in grams. From our sentence above, I'm saying that 1 mole of carbon is equal to the atomic mass of it in grams is equal to 12.01 grams. So we'll prove this. So we start with our given quantity, 1.000 moles, and then we convert to atoms using our quantity 6.022 times 10 to the 23rd atoms equals a mole. By the way, that is Avogadro's number. Okay, now moles are canceling and we have atoms. Next step is to use the atomic mass of carbon, which is 12.01 U per atom. We write it so atoms cancels. Our last quantity is to convert from atomic mass unit to grams. That conversion is 1.661 times 10 to the minus 24 grams per U. So we have U canceling. The only unit we're left with now is gram, and the number is 12.01 grams. So what we have is, in 1 mole of carbon, we have 12.01 grams. 12.01 grams equals 1 mole of carbon. We also could say 12.01 U equals 1 atom of carbon. It depends what scale we're on. If we're on the lab scale, we're talking moles and grams. So that number on the periodic table, that 12.01 for carbon, is the grams per mole. But if we're on the atomic scale, the atomic mass unit scale, we would say that 12.01 is the atomic mass unit per atom. For hydrogen, we see rounded to 3 sig figures, the number 1.01. So that would be 1.01 grams per mole of hydrogen, or 1.01 U per atom of hydrogen. When we're considering that quantity in grams per mole, that's called the molar mass. So the molar mass of carbon is 12.01 grams per mole. For hydrogen is 1.01 grams per mole of hydrogen. So these are molar mass. Often we abbreviate molar mass MM, and they are the grams in 1 mole of the substance. So once again, for carbon, the molar mass is 12.01 grams per mole. And for hydrogen, 1.01 grams per mole. So those are on the lab scale. On the atomic scale, it would be same number, U per atom. The periodic table, as we've talked about, shows the molar mass of each element. They are combined to calculate the molar mass of a compound. For example, let's calculate the molar mass of CH4. So that would be the molar mass of 1 carbon plus 4 times the molar mass of hydrogen. So we have 12.01 grams per mole plus 4 times 1.01 grams per mole. The molar mass for CH4 is 16.05 grams per mole. Calculate the molar mass of NH3. NH3 is ammonia. So come back and do that problem. Here's an example. We have 250 grams of NH3, ammonia. How many moles are present? How many molecules are present? In the example above, we would have calculated the molar mass of ammonia to be 17.04 grams per mole. Okay, so in this problem, we start with the 250 grams, and then we write the conversion beside it such that grams cancel out. So we're going to put 17.04 grams in the denominator, mole in the top. We would see on our calculator perhaps 14.67. We would round that to 15 moles. 15 because we have 2 sig figs and 250. How many molecules are present? So now we take the moles, and notice that we're midway through a calculation now, so we go back to the 14.67 number, moles, and then we write Avogadro's number conversion beside it such that moles cancel out. So 14.67 moles times 6.022 times 10 to the 23rd molecules per mole gives us 8.835 times 10 to the 24, which we round to two figures because now we're reporting the answer, 8.8 times 10 to the 24 molecules. Here's an example to come back to. How many grams of ammonia are present in 2.5 times 10 to the 23rd molecules of ammonia? Our next topic is percent composition, and it's percent by mass. We calculate the mass percent of each element in a compound by comparing the mass of each element in 1 mole of compound to the total mass of 1 mole of compound. Calculate the mass percent nitrogen and mass percent hydrogen in NH3, ammonia. Alrighty, so percent is part over whole times 100. If we were after not the mass percent nitrogen in ammonia, but the mole percent nitrogen in ammonia, we would say, well, ammonia is composed of 1 N and 3 H's, so the whole would be 4, the part for nitrogen would be 1, times, so we'd have 1 over 4 times 100, it would be 25% nitrogen by mole. But we're after the mass percent, so we have to take into account not just how many nitrogens are there, but what the mass of nitrogen is. Okay, so the percent nitrogen is the mass of nitrogen in a mole of compound divided by the mass of 1 mole of compound times 100. In NH3 we have 1 mole of N, so we take 1 mole N times 14.01 grams per mole, and we have 14.01 grams of N as our part. The molar mass from above is 17.034 grams per mole. So that's the whole. So we take 14.01 grams divided by 17.034 grams times 100. We get the percent N to be 82.25%. The percent H is the mass H in 1 mole of compound divided by the mass of 1 mole of compound times 100. In ammonia, in 1 mole of ammonia, there are 3 moles of H. So we take 3 moles times 1.008 grams per mole. I'm using 4 sig figs for the molar mass of H so that I can report 4 in the end. We get 3.024 grams of hydrogen. That's the part. The whole is the molar mass, 14.034. Okay, grams per mole. All right, so the percent H, not N, percent H is 3.024 grams divided by 17.034 grams times 100, 17.75%. Another way to get that is to realize that the percent N plus the percent H equal 100, so we could determine the percent H from 100 minus 82.25 and get 17.75% H. All right, now calculate the percent carbon, the mass percent carbon and mass percent hydrogen in CH4. Our next section is empirical and molecular formula. The empirical formula of a compound is the smallest whole number ratio of elements making up the compound. So it's the smallest whole number ratio. CH, that's an empirical formula for some compounds. The compound could be C2H2. Notice that the simplest, smallest whole number ratio is 1:1, 1 carbon for every 1 hydrogen. It could be C6H6, which is another compound with the ratio, the simplest ratio of 1:1. So the empirical formula is just the smallest ratio of those elements making up the compound. It doesn't mean that is how many atoms of each of those elements make up the compound. CH is an empirical formula. The real compound could be C2H2 or C6H6. The real compound, it's described by its molecular formula. Molecular formula tells us how many of each of those atoms actually there are in the molecule. The empirical formula is simply the simplest ratio. Another empirical formula is HO. That compound, for example, could be peroxide, H2O2. Another empirical formula is NO2. So that's saying one N for every two O's. Now, NO2 is a compound. It really is. So maybe that empirical formula is the molecular formula, but it could also be N2O4 because that's also got the 1:2 ratio. We'll go through the steps by considering this problem. A compound is 52.12% carbon, 13.16% H, and 34.72% O by mass. Calculate its empirical formula. So the steps are to assume a 100-gram sample and convert from percent to grams. 100-gram sample we've assumed because if it's 52.12% carbon in this 100 grams, we have 52.12 grams of carbon. We have 13.16 grams of hydrogen. We have 34.72 grams of O. That's step one. Step two is convert from grams to moles, because it's only moles that we can compare. So 52.12 grams of carbon divided by the molar mass of carbon gives us 4.340 moles of C. 13.16 grams of H divided by the molar mass of hydrogen gives us 13.06 moles of H. 34.72 grams of O divided by the molar mass of O gives us 2.170 moles of O. Now, those numbers are showing us the mole ratios between the carbon, the hydrogen, and the oxygen. But they're not whole numbers. What we want is to manipulate them so that we end up with whole numbers. The first thing that we do, that's step 3, is to divide by the smallest number. Of those three numbers, our smallest number is 2.170. When we do that, we make at least one of those numbers into 1. So that's all on an effort to get whole numbers. Alrighty, so 4.340 moles of C divided by 2.170 is 2.000 moles of C. 13.06 moles of H divided by 2.170 is 6.018 moles of H. And 2.170 moles of O divided by 2.170 is 1.000 moles of O. We basically have whole numbers, 6.018 close enough to 6. So we basically have whole numbers. There is a step 4, which we do if needed. So step 4, if needed, multiply by a factor to make the numbers into whole numbers. Well, we have whole numbers, so we don't have to do this step. So we have 2 moles of C to 6 moles of H to 1 mole of O. We would write the empirical formula as C2H6O. And what that's telling us is the ratio of C to H to O. It is not telling us that that compound is only that big. It might be that big. It might be twice that big. Okay, determine the empirical formula of a compound with 30.45% N and 69.55% O by mass. Alrighty, so more on that step 4 that we didn't have to do in this problem. If the mole numbers from step 3 come out, for example, 1.5 mole of C, 3.0 moles H, and 1.5 moles of O, then in step 4, we would multiply all by 2 to get whole numbers. 3 moles of C, 6 moles of O, 3 moles of C, 6 moles of H, and 2 moles of O. And the empirical formula would be then C3, H6, O2. Because we don't write an empirical formula with half integers like C 1.5, H3O. In homework problems, or problems in general, if you get a number ending in 0.25, when you multiply in step 4 by 4, you would get a whole number. If, on the other hand, it ends 0.33, multiply by 3 to get a whole number. If 0.5, like the example we just looked at, multiply by 2. If 0.75, multiply by 4. So here's another one for you to work on. Determine the empirical formula of this iron and oxygen compound. Molecular formula. This is how the compound actually looks. It shows the actual number of each element in the compound. For example, C2H2 would be a molecular formula for CH. H2O2 would be a molecular formula for HO, and so on. N is the factor that we multiply the empirical formula by to get the molecular formula, where N is equal to the molar mass, which we have to be given in the problem, divided by the empirical formula mass. For example, the molar mass of a compound with empirical formula NO2 is 92.02 grams per mole. What is the molecular formula? So how big is it truly? The empirical formula mass is 1 nitrogen, so 14.01 plus, and there's 2 O's, so 2 times 16.00, equaling 46.01 grams per mole. So that's the empirical formula mass for NO2. N equals molar mass over empirical formula mass. So we have 92.02 grams per mole over 46.01 grams per mole, and we get the number 2. So the compound is really twice as big. It's really N2O4. So here's an example for you to work with, to come back to later, actually 2 examples. Next we have chemical equations. We use chemical equations to describe a chemical reaction. A chemical reaction, we have reactants yielding products. Let's take this chemical reaction here, C8H18 plus O2 yielding CO2 and water. So what we're told there is what reacts and what forms. We can give more information if it's relevant. For example, we could give the state or the phase that each substance is in. If it's in the gas phase, we put a G in parentheses right beside the molecule. If it's liquid, L in parentheses, a solid, S in parentheses. If it's aqueous, we put a Q in parentheses. Aqueous means the substance is dissolved in water. It's not a liquid itself, it's rather fully dissolved into the water. Sugar, we've probably all dissolved that in water. Sucrose has the molecular formula C12H22O12. It's a solid at room temperature. When we dissolve it in water, and notice I put water over the yield sign, we get C12H22O12 aqueous. It disappears into the water surrounds the molecules. It's now aqueous. So we can put those subscripts in: C8H18, a liquid, so there we go, O2, a gas, CO2, a gas, H2O, a liquid. More information we can put, and we have to do that if we're going to make calculations, is we can make the chemical reaction, as we say, balanced. And the number of each type of atom on the left side must equal the number of that same type of atom on the right side when we have a balanced reaction. We make each type of atom on the two sides equal by inserting coefficients called stoichiometric coefficients in front of the compound. That is to say, we fill in those blanks. Let's put the invisible 1 in the first blank. That's telling us 8 carbons, 18 hydrogens on the left side. So we have to have that same thing on the right side. So we would put a big 8 in the CO2 blank. We would put a 9 in the H2O blank because we have H2O, so 9 times 2 is 18. On the right side, we have 8 times 2, 16, plus 9 O's. We have 25 O's on the right side. So we need 25 O's on the left side. On the left side, we have O2, so we can write 25 over 2. Now we have 8 C's on both sides. We have 18 H's on both sides. We have 25 O's on both sides. But we don't like seeing a half integer as a stoichiometric coefficient, so we would multiply by 2. So we would have our fully balanced reaction, 2C8H18 liquid plus 25 O2 gas yields 16 CO2 gas plus 18 H2O gas. So here are some examples for you to balance. Stoichiometric calculations. From a balanced chemical equation, we can determine the moles or masses of products produced from a given number of moles or masses of reactants. Let's take this reaction, 2C4H10 plus 13O2 yielding 8 CO2 plus 10 H2O. That equation tells us that 2 moles of butane, which is C4H10, requires 13 moles of oxygen to produce 8 moles of carbon dioxide and 10 moles of water. These coefficients give us mole ratios between compounds. So the 2 to 13, the 13 to 8, and so forth, those are what we call mole ratios. Some of the mole ratios are 2 moles C4H10 correspond to 13 moles O2. 2 moles C4H10 equals 8 moles CO2. 2 moles C4H10 equals 10 moles of H2O. Or we could say 13 moles of O2 to 8 moles of CO2, 8 moles of CO2 to 10 moles of water, 2 moles of C4H10 to 10 moles of water. We can jump around any way we need to within a chemical reaction with these mole ratios. They are what allow us to go from moles of one substance to moles of the other. So we can go between moles of reactants, between moles of products, or between reactants and products, however we need to. Here's an example. How many moles of CO2 are formed from 3.6 moles of C4H10? So we take our 3.6 moles C4H10 and we write the mole ratio between the two we're interested in, the C4H10 and the CO2. We put the numbers 2 and 8 in the right spot, and we have 2 moles of C4H10 in the bottom. That gets us 14 moles of CO2. Here's a few problems for you to work on. But we don't count moles. Rather, we count by weighing. So we start with grams and so forth. But we can only jump between compounds in an equation via their mole ratio. To get to moles from grams, we use molar mass. For example, if we have chemical A plus chemical B giving us chemical C, and we're given grams of A, well, we have to go from grams of A to moles of A with the molar mass of A. Then we can jump from moles of A to moles of C with the mole ratio between C and A. And then, if we are supposed to report the answer in grams of C, then we would use the molar mass of C for that last conversion. Alrighty, so going back to our same chemical reaction, our problem is how many grams of O2 are needed to react with 0.42 grams C4H10. So we start with our given amount, 0.42 grams C4H10. We convert to moles, so we divide by the molar mass of C4H10. We put the grams in the bottom, so grams cancel. Now we have moles of C4H10. Now the mole ratio between C4H10 and O2 is what we do next. So we have 13 moles O2 over 2 moles C4H10. Moles of C4H10 have canceled. We have moles of O2, but we want grams, so we use the molar mass of O2, 32.00 grams per mole, to give us 1.5 grams of O2 are needed. Alrighty, so there's a few other examples for you to work with. Our next section is limiting reactant. We're going to talk about it by looking at a very simple example involving everyday stuff, that is, making of a sandwich, following our sandwich recipe. It's all very obvious. I know you will hardly need to go through steps, but I'm dissecting it. I'm going through each step because when we work with a chemical reaction, we will have to go through each step. It won't be so obvious. Okay, so let's say that we make a sandwich following this exact chemical sandwich reaction. 2 breads plus 1 cheese plus 3 meats equal 1 sandwich. The bread, cheese, and meat are the reactants, and the sandwich is the product. In our example, we have unlimited bread, 4 slices of cheese, and 9 slices of meat. How many sandwiches can we make, and which reactant limits the number of sandwiches we can make? This reactant is called the limiting reactant, LR. Yeah, it's obvious. I'm sure you could say right off, well, the meat limits, it allows for us to make 3 sandwiches and there's 1 piece of cheese left over. Let's go through the steps, however. So the steps are to assume the reactant in lesser amount. For us, it's the cheese. There's 4 slices of it versus 9 of the meat and unlimited bread. So assume the reactant in lesser amount is the limiting reactant. Then determine the amount of the other reactant needed to use up all of the assumed limiting reactant. Okay, so we assume the cheese is limiting reactant. We figure out how many pieces of meat we have to use to, or have, to use up all the cheese. So we write our ratio, our mole ratio between the meat and the cheese, and we get that we need 12 pieces of meat. Next, we compare this quantity to the actual amount of meat present. If more meat is present, then meat is in excess, and the initial guess that cheese is the limiting reactant is correct. If less meat is present, then meat is the limiting reactant, and it will run out and limit the amount of sandwiches. Since more meat is needed than is present, 12 versus 9, meat is the limiting reactant. So we use the real limiting reactant to determine the amount of sandwiches produced. So we take the 9 pieces of meat that we have. Now we're using the ratio between the meat and the sandwich, 1 to 3, and we have our 3 sandwiches. how much cheese is used and how much is left over. Okay, so how much cheese did we use with those 9 pieces of meat? We take the 9 meats, multiply by the ratio between cheese and meat, 1 to 3, and we get that 3 pieces of cheese were used. We subtract that from what we had, 4, and we get 1 piece of cheese is left over. Okay, so simple steps with that sandwich. Now let's apply them to a less obvious chemical reaction. So there's our reaction, the same one we've been working with. In our problem, we have 6.0 moles of C4H10 and 20 moles of O2. Which is the limiting reactant, and how many moles of CO2 are produced, and how many moles of the excess reactant are left over? So we assume the smaller of the two, the C4H10, is the limiting reactant, and we figure out how much of the other one is needed to use it all up. 6.0 moles of C4H10 times the ratio 13 moles O2 over 2 moles C4H10. Moles of C4H10 cancel, and we get the number 39 moles of O2 are needed to use up all the C4H10. We compare 39 to 20 and we see that we don't have that much. That means the O2 is the limiting reactant. So now we calculate with it. We take our 20 moles of O2 and we multiply by the ratio between the CO2 and the O2. So we're multiplying by 8 moles CO2 over 13 moles of O2. Moles of O2 cancels and we get 12 moles of CO2 are produced. C4H10 is in excess. That is, in our beaker, call that a beaker on the right, we have products, CO2 and water, and we also have C4H10 in the end of the reaction. Okay, to figure out how much C4H10 is used, we take the 20 moles of O2 that we used, and we multiply by the ratios between the O2 and the C4H10. So times 2 moles of C4H10 over 13 moles of O2, that gives us 3.1 moles of C4H10 were used. What's left over? So we do 6 minus 3.1 and we get that 2.9 moles of C4H10 are left over. Okay, so here are the steps to the limiting reactant calculation problem. Step 1, find the moles of each reactant. Sometimes we're given grams instead of moles, so we have to find the moles of each reactant. Step 2, determine the limiting reactant by assuming it is the reactant with the smaller number of moles. Let's call that compound A. Then determine the number of moles of the other reactant, compound B, needed from the mole ratios. Step 3, compare this to the actual moles of B. If more B is present, B is in excess, and the initial guess that A is the limiting reactant is correct. If less B is present, B is the limiting reactant and determines the amount of product formed. Step 4 is to use the real limiting reactant to determine whatever quantity is asked for. Often it's the amount of product formed. Okay, so here's an example. Same reaction. Now we have 25 grams of C4H10 and 34 grams of O2. Which is the limiting reactant and how many grams of CO2 are produced? So walking through the steps, and definitely come back and look slowly and carefully at this problem, what we have to do is figure out how many moles of C4H10 we have and how many moles of O2 we have. So we're using the molar mass, and then we look at those two numbers and choose the smaller of the two to figure out how many moles of the other one would be needed to use up all of that. And then we compare that quantity to the amount we have, and we determine which is the limiting reactant. Once we know which one it is, then we go with that many moles of the limiting reactant, and we convert from with the mole ratio to the moles of the product, and then finally to the grams of the product. The last thing asked for here is how many grams of the one in excess is left over. So come back and go through that problem yourself. Here's another problem for you to work on, this one here. Our next section is the percent yield. Theoretical yield is the calculated mass of product that could theoretically be obtained. It's the mass of the product that is the maximum possible amount, the theoretical amount that could be obtained. In practice, when we actually do the experiment, we usually obtain less than that amount. The actual yield is the amount actually obtained when we do the experiment. We put these two together and calculate the percent yield. The percent yield is the actual yield divided by the theoretical yield times 100. The percent yield gives us an indication of how good our experimental procedure was. We know we should be able to make a certain amount. That's the theoretical yield. We do the experiment and we weigh the amount of compound that we actually make, and that's the actual yield. The closer percent yield is to 100, the better we have done the experiment, and the better is our procedure. So here's an example. 4 Fe plus 3 O2 yield 2 Fe2O3. Given 7.8 grams of iron, calculate the theoretical yield of Fe2O3. Now, there is no mention of the amount of oxygen, so we assume that is in excess. So the 7 grams of iron, that would be our limiting reactant. So we have to go from 7.8 grams of iron to moles of iron. So we're dividing by the molar mass, 55.85 grams per mole. And then we jump from moles of iron to moles of Fe2O3. So we have 4 moles of iron in the bottom, 2 moles of Fe2O3 in the top. And finally, we want grams. Theoretical yield is grams. So we figure out the molar mass of Fe2O3. It's 159.70 grams per mole. We multiply by that, and we have 11 grams of Fe2O3. That would be the maximum amount that we could make. That's the theoretical yield. When the reaction was actually done, 9.8 grams of Fe2O3 were actually obtained. Calculate the percent yield. So we take the actual yield, 9.8, divide by the theoretical yield, 11, times 100, and we get the percent yield to be 89%. Here's an example for you to do. Same reaction. Now we're given grams of both reactants. So what we have to do is convert each one into moles, and then we have to go through the limiting reactant steps to determine how much product is made from the limiting reactant. And here we're told the amount of product that were actually obtained, and we're calculating the percent yield. In our last part, we just have the answers. So, as always, go through this video, pausing, starting, whatever works for you, again, however many times it helps you. Go through the handout, make sure that you've done all the examples and are competent at those. Read chapter 3 in your textbook, go through all the assigned homework problems,